Hi, and welcome to this review on similar triangles. Today we're going to explore how to identify similar triangles and how we can use that knowledge to solve a very popular kind of geometry problem. Let's start with a simple definition. Similar triangles are triangles that have the same shape. That means that we'll have the same three angles. But here's the twist. Similar triangles don't have to be the same size. So if you take a copy of the triangle and dilate it to twice its size, it will still be similar to the original triangle. Notice that the two triangles have the same shape and proportions. That's because they have the exact same angles, which is what makes them similar triangles. This is the angle-angle-angle, or AAA method of determining similarity. It should be noted that anytime you dilate a triangle, you end up with two similar triangles. Since we know that these two triangles are similar triangles, we can express this in math notation like this. Triangle ABC is similar to triangle A', B', C'. Okay, but what if we didn't start by dilating and don't know all the angles? Is there any other way to tell if two triangles are similar? Let's look at an example where we only know the lengths of the sides of two triangles. These two triangles appear to be the same shape, but remember that in geometry we can't always trust our eyes. We need to prove that they are the same shape, and we can do that by checking to see if their sides are in proportion to each other. We set up our proportions by setting up ratios or fractions of the corresponding sides and setting them equal to each other like this. We'll have the side lengths for triangle ABC be the numerators, and the lengths for triangle DEF be the denominators. It would work just as well if we switched it around. It's very important to label proportions and to make sure we put all their numbers in the proper place. So what does this proportion do for us? Well, we need to test to see if it's true. In this case, we can do that by reducing each of these fractions to their simplest form. We can see that 3 goes into the top and bottom of 6/9, so we can reduce it to 2/3. 4 goes into 8/12, and 5 goes into 10/15. When we reduce those two fractions, we also end up with 2/3. In reduced form, our proportion looks like this. This is proof that all of our sides are in proportion. If all the sides are in proportion, then we know that our triangles are in proportion. This is the side-side-side, or SSS, method of proving similarity. So now we can say that triangle ABC is similar to triangle DEF. Instead of reducing, we could also check to see if the ratios are in proportion by converting each ratio to a decimal by dividing the top by the bottom of each. In this case, 6 divided by 9, 8 divided by 12, and 10 divided by 15 would have given us the same decimal value, which is 0.6 repeating. So now we know that if all the angles are the same, or if all the sides are in proportion, our two triangles are similar. There is one more method of proving similarity, called side-angle-side, or SAS. This is where we know the two triangles have one angle that is the same measure, and that the two sides coming off of that angle are in proportion. Let's look at our last two triangles, but instead of knowing all three sides, we will only know two sets of corresponding sides along with the angle between them, like this. We can see that the angle between the two measured sides is labeled with a square, which we know means that it's a right angle and therefore 90 degrees. Since that angle is the same in both triangles, we just need to check to see if the two adjacent sides are in proportion, like this. Reducing the fractions again results in them being 2/3, so the sides are in proportion. Since the angle between those sides is the same, or congruent, this triangle is similar. Okay, so what can we do with this ability to recognize similar triangles? You may have seen it before, but here's the classic height of the tree problem. Here's what we know. The tree and the flagstick are both standing straight up perpendicular to the ground. They are each casting a shadow from the same light source, the sun. The rays coming from the sun are straight lines shining on the objects at an angle. The ground is flat and can be considered a flat plane, which means that any 2 points on it can be connected with a straight line. That means I can draw two triangles over this drawing, like this. Now let's keep our triangles, but lose the pretty scenery. Next, let's label all the points so we can reference them. It doesn't matter what letter we use for each point. We also know that angle B and angle D are right angles since the flagstick and the tree are pointing straight up perpendicular to the ground, so we'll label that too. Since we know that angle A is the same for both triangles, and that angles B and D are both right angles and therefore congruent, that means that angles C and E are also congruent. Why? Because the interior angles of a triangle must add up to 180 degrees. So if A is 30 degrees and B and D are 90 degrees, then C and E will end up being 60 degrees. Now we know they are similar triangles using the AAA method of proving similarity. Now we can get to the fun part and use these triangles to find the height of the tree. First, we'll need to take some measurements. We need to measure the flagstick, the length of the shadow of the flagstick, and the length of the shadow of the tree. Fortunately, these are all easy to do. A standard golf flagstick is 7 feet tall. The shadows are on the ground, obviously, so we can measure them with a long tape measure. Then we can add them to our triangles. Since the sides of similar triangles are always in proportion, we can set up a proportion with all rows and columns labeled. We don't know either of the diagonal sides, but we don't need them for this type of problem. We know the ground sides of both triangles, and we know the height of triangle ABC. We can place a variable for the height of the tree, which is line segment DE in our triangle. Now we just use cross products to solve. Taking cross products results in the equation 9x equals 45 times 7, or 9x equals 315 after we multiply 45 and 7. Dividing both sides by 9 gives us x equals 35, so our tree is 35 feet tall. Okay, now that we've covered everything, let's do a quick recap. Similar triangles are triangles that have the same shape. There are 3 ways to prove that 2 triangles are similar. The AAA method of similarity is when all 3 proportions of the triangle are the same. The SSS method is when all 3 sides of the triangles are proportional. And finally, the SAS method is when the 2 triangles have one angle that is the same measure, and the 2 sides coming off that angle are in proportion. I hope this review is helpful. Thanks for watching, and happy studying.